In section 2.6, we will introduce matrices. So firstly, we will define what is a matrix and something about matrix arithmetics, for example, the addition or multiplication of matrices. And then we will see the definition of a special form of matrix, for example, transpose or the power of the matrix. In the last part, we will introduce a very special matrix, which is called 0-1 matrices. Okay, matrices is a very useful data structure you can use in a lot of research area. For example, linear transformation. Okay, so when you go to the graduate school for computer vision or image processing, you will apply a lot of different linear transformation to transform the images into different types of images. So in that case, we will use the form of matrix to define the rotation or translation using the matrix. So you will see the application of matrix is a lot. Okay, in discrete mathematics, you will see how to express the graph or the connectivities of a graph using matrix. For example, how many edges or how many vertices are defined for this graph. We will use the matrix representation to define the connection or connectivity of the graph. Okay, we also a lot of applications, for example, transportation system or communication networks. You can use a matrix to build the model to represent different systems. Okay, so I think it's chapter 10 or chapter 11. You will also see we will apply different algorithms using matrix for further analysis for graph. Okay, so firstly, let's define what is a matrix. Matrix is a rectangular array of number using m rows and m columns. So usually we will call m by n matrix. Okay, so when we call this matrix m by n, that means we have m rows and m columns. Okay, so you will see the plural of matrix a lot, matrices. Okay, so if n equals m, then we call that square matrix. In this case, we have a 3 by 2 matrix because we have 3 rows and 2 columns. So it's a 3 by 2 matrix. Okay, once the number of row equals the number of column, then we call that square matrix. For example, we will have 2 by 2 matrix or 3 by 3 matrix. They are also square matrix. Okay, when we define the equality of two matrices, the condition is they have the same number of rows and same number of columns, and the corresponding entries in every position are equal. Okay, that means if we have one 3 by 2 matrix and we have another 3 by 2 matrix, okay, the first thing is the number of row and number of column should be equal. And then each element or each entry should be equal. Then these two matrices are equal matrices. Okay, so let's see the notation of matrix. If the matrix is m by n, then we can define the notation for each entry. So for example, this element, we call that entry or element of the matrix. Okay, we can use A11, A12, A1n, or A21, A22 to label the position of each entry of the matrix. Okay, So the index, we will use ith row and jth column as its index. For example, if we call this entry A12, that means it's the first row and the second column. Okay, so we will use Aij to represent the position in each position of the matrix. Okay, next let's see how to add two matrices. If we have one matrix A and another matrix B, we use Aij and Bij to represent the matrix. Okay, so the sum of A and B we will denote by Aij plus Bij, which means we use corresponding position and add these two elements together to form a new matrix. Okay, so I believe you must be very familiar with the addition of matrices. So maybe we can just see one example. For example, we have two 3 by 3 matrices. The addition will use the corresponding position and add them together, okay, to have the new entry in the new matrix. Okay, next you need to notice that if the matrix with different size, that cannot be added. For example, you have a matrix 3 by 2 and another matrix 2 by 3. Their dimensions are not equal, so you cannot add these two matrices. Okay, the multiplication of two matrices, we can define the ij element. Okay, so when we calculate the ij element of the new matrix, basically we use ith row of A and jth column of B to calculate Cij in the new matrix. Maybe we can see the example. Okay, so once we have two matrices A and B, and we will calculate the multiplication of A and B. So the element Cij in this position, okay, we will use ith column, ith row of A and jth column of B. So we will multiply AI1, B1J. So this element and this element. Okay, and then we multiply AI2 and B2J. And then we add all these products. Okay, then we will have Cij. One thing you need to notice that matrix multiplication is not commutative, which means if you multiply 2 by 2 matrix AB, then AB will not equal to BA. Okay, you can use this example to verify that multiplication is not commutative. So if you multiply A and B, you will get 3, 2, 5, 3. But BA 4, 3, 3, 2. So these two matrices are not equal. Okay, next one is the identity matrix. Okay, identity matrix is defined for square matrix n by n. So we will use delta as the notation of the entry. So delta ij means each element, you can use different index row I and column index j. Okay, for identity matrix, we will define for the diagonal element. If I equals j, then delta ij equals 1. Otherwise, the other elements are all zeros. Okay, so if we have an n by n matrix, this is an identity matrix. So we will have all its diagonal elements are 1, the others are 0. Okay, we call that identity matrix because if you multiply identity matrix to any matrix A, and then it will become itself. Okay, so A can be n by n or other dimensions. So if it's n by n, you can multiply the identity matrix In. So if the matrix n by n, you can also multiply the identity matrix in the left-hand side of A. So it will In. So this is a n by n matrix. You can multiply n by n, so that makes it a n by n matrix. Okay. We can also define the power of square matrix. So if A is a n by n matrix, then we can multiply the matrix multiple times. So if we multiply A many times, for example, R times, that will be A to the power of R. Okay. Okay, next, let's see the definition of transpose of matrix. Okay, if A is defined by Aij is a n by n matrix, then the transpose of A, we will change rows and columns of A. For example, the transpose of A will be Bij. The element or entry of Bij equals Aj. Okay, just switch the index of row and column, and then it will be a transpose matrix. For example, if we have a 2 by 3 matrix, okay, so this is the first element A11. This is the second element A12. Okay, the transpose of the matrix, so we will have this one is A21. Okay, so basically you can put A12 to the position of A21, then it will be a transpose matrix. So after the operation of transpose, the matrix will become a 3 by 2 matrix. Okay, next let's see a very special matrix which is called symmetric matrix. Okay, if a square matrix A equals its transpose, then it's symmetric. Okay, so we call that symmetric because in this matrix, Aij equals Aji. So we can see the first thing is the symmetry matrix is defined for square matrix. Okay, so if this matrix is 3 by 2 or 2 by 3, then we cannot define its symmetry matrix. Okay, because you cannot use the definition Aji equals Aij for any matrix that is not squared. Okay, so in this case, let's check why this matrix is symmetric. Because this is A12, this is A21. Okay, they are equal. And this element is A23. So this is A32. They are equal. Okay, so we can check this matrix, which is a symmetric matrix. Okay, next let's define a very special matrix, which is 0, 1 matrix. Okay, we call that 0, 1 matrix once all of its entries are either 0 or 1. Then we call this matrix 0, 1 matrix. So we won't have values other than 0 and 1. Okay, 2, 3, 4, 5, we don't have values like that. Okay, only 0 and 1 in this matrix. Then we call that 0, 1 matrix. Okay. The 0 matrix, we can define Boolean arithmetics for 0, 1 matrix because we only have 0 and 1. Okay, so if we want to apply the Boolean operation AND by B1 and B2, then if B1 and B2 are all 1, then B1 and B2 are 1. Otherwise, it's 0. Okay. We can also define B1 or B2. Okay. So if we have B1 equals 1 or B2 equals 1, then B1 or B2 is 1. Okay. I think this concept is very similar to and or that we have learned in chapter 1. Okay, we call that Boolean arithmetic, which is defined for 0, 1 matrix. Okay, follow the definition of Boolean operation, then we can calculate the join or meet of two 0, 1 matrices A and B. Okay, so let's see the definition of join of two matrices. The join of Aij, the ij's entry is defined by Aij or Bij. Okay, then we call that the join of A and B. Okay, the meet of A and B, which we calculate ij's entry using Aij and Bij. Okay, that's the meet of A and B. So let's see a quick example. The join and the meet of two 0, 1 matrices. So if we have A and B like this, the join of A and B, okay, we find the corresponding element and calculate the join of these two elements. So the join 1 and 0, so 1 or 0 is 1. Okay, the second element 0 and 1. Okay, so 0 or 1 is also 1. Okay, follow this operation, you can calculate all entries of the join matrix of A and B. Okay, let's see the meet of A and B. Okay, meet we will calculate AND operation. Okay, so first element A and 0, when we AND these two values, the results will be 0. Okay, if we AND the 0 and 1, okay, 0 and 1, after the AND operation, we will have 0. Okay, so this is how to calculate the join and meet of two 0, 1 matrices. Okay, we can also define another operation, which is Boolean product of 0, 1 matrix. Okay, the Boolean product, we will use a spatial notation like this. Okay, so basically the calculation, just like the multiplication of two matrices Cij, except for we only use meet and join operations to calculate Cij. Let's see this example. If we have A, which is a 3 by 2 matrix, and B is a 2 by 3 matrix. So let's see what is the Boolean product of these two matrices. Okay, A is here, B is here. So let's see the first element of the Boolean product A and B. Okay, so the first element, we use the first row and the first column of A and B. Okay, so the corresponding element A, 1 and 1. Okay, we use the meet operation, AND operation, and 0 and 0, AND, and then we OR these results. Okay, then we can see N1 and 1 is 1. Okay, 0 and 0 is 0, and we OR 1 and 0, which is 1. Okay, so maybe we can see another position, for example, this one. Okay, so for this one, we use the second row of A and first column of B. Okay, so we will have 0 and 1. Okay, and 1 and 0. And then we OR the results. Okay, so here we have 0 and 1, 1 and 0, and OR the results, then we will have 0 and 1, and we OR the results, which is also 0. Okay, so the concept of Boolean product is very similar to the multiplication of a normal matrix A and B. Okay, just replace the addition and multiplication using AND and OR, then it will be Boolean product of two 0, 1 matrices. Okay, let's see the Boolean power of 0, 1 matrix. So the definition of Boolean power is just like the calculation of power of general matrix. So if we have the matrix A like this, so once we need to calculate A to the power of n, so we can calculate step by step. First, we can calculate the A to the power of 2. So we need to calculate the Boolean product of A and A. That will be the A to the power of 2. Okay, so we already know how to calculate the Boolean product A and A. Okay, so after that, we can calculate A to the power of 3 using A to the power of 2 Boolean product A. So by this step, you can calculate any n, positive integer n, to have the Boolean power of 0, 1 matrix. Okay, so this will be the brief introduction of section 2.6. It's just a very simple definition and calculation of matrix. So in the later chapters, you will see we will use 0, 1 matrix a lot for example, for trees or for graphs, or when we calculate the path of the graph, we will use a lot of different algorithms to represent the graph using 0, 1 matrix. And we can also calculate the path of the graph using 0, 1 matrix. Let's see what we will have learned in the later chapter.